This is what I'm looking for. Without Stat Key, you have to learn to either do a lot of complicated calculations yourself or to use tables like this. So rather than have me trying to teach you to use these tables from a distance, we are going to use Stat Key for some of your calculations. And one thing we need to do is go back to the concept of a bell-shaped distribution and z-scores. So let me share a whiteboard here. And because this course is designed to cover things a little bit differently than your e-text does, the e-text, and which does not have an interactive video that just covers what we're covering today, which is the distribution, sampling distribution of a proportion. That's why there's not an interactive video for it. So we're going to go with what we're doing today in class. So here is my attempt at drawing a bell-shaped distribution. Okay, and when we were talking about distributions, we often talked about the mean, and we talked about standard deviations and how you could measure standard deviations above and below the mean. For instance, we might look at the average age in this class, and I'm taking a wild guess because I didn't get enough responses to, nope, not where I was going, to the survey to know. So maybe 21.3 with a standard deviation of, let's say, 4 years. So 21.3 years and a 4-year standard deviation. So this would be 25.3 and 29.3. And going the other way, 16. I keep wanting, no, I did do 4. Okay, yeah. 17.3. And 13.3. Check me on this because I'm trying to do it quickly here and may well make a mistake. 4 and 4. 4 and 4. Okay. So within 2 standard deviations, above and below the mean would fall 95% of your ages. And do that in a different color so it shows up. Okay. But then we talked about how you can convert this to a z-score to find out, say, if one of you is 18.1 years old. So somewhere in here. 18.1. I'll make it big and fat so I cover it. What would be the z-score for 18.1? Well, you could take the 18.1, subtract the mean, and divide by the standard deviation. And could somebody do that on a calculator for me real quick? 18.1 minus 21.3, get that value, and then divide it by 4, or put it all in at once with parentheses around the numerator. Minus 0.8, good, and confirmation, thank you. So instead of using the values that are there, I could have, let me put this in blue, and let me make a little more room by getting rid of that sample. And actually that would be a population mean. if when I had 21.3, if I had all of the data for all of you. I only received a small sample, so it wasn't even worth working with. But anyways, the z-score would be minus 0.8. So I wasn't that far off. This standard deviation is minus 1 standard deviation below the mean, which would have a z-score of 0, because the mean minus the mean is 0. This standard deviation would be minus 2, and here we would have minus 3 standard deviations. Here, 1, 2, and 3. Okay, so I'm going to straighten this up a little bit here. So minus 1, minus 2, minus 3. And this is the z-score for our 18.1 year old student. So when we look at a distribution like this in terms of standard deviations and z-scores, how many standard deviations a value is above and below the mean, we can actually just make all of this rather more theoretical and just work with what we call a standard normal curve. And every bit of data that is within this curve can be converted to a z-score. So we actually call this also a z distribution. Okay, so the standard normal curve is sometimes called a z distribution. I should write that out. Okay, so that's the letter we use to represent it. There's also another letter that's often used to represent any normal curve. Okay. So for any normal curve, or any approximately normal curve, I should say, I'll show you why in a moment. So any approximately, okay, normal curve can be described 3 ways. You need to say that it is approximately normal, and instead of bell-shaped now, I'll write this down at the corner. We will refer to that as approximately normal. And any approximately normal curve can be symbolized with an n and with 2 numbers, the mean and the standard deviation. So for this curve, what I originally had up there, the mean was 21.3 and the standard deviation was 4. So there's 1 standard deviation above the mean, the 4 years here. Any questions so far? Because I really need some talk here, since I'm trying to give you so much information that your book takes a couple of chapters to do. So when you're looking through your text now, you will see this, and on the videos. N means you have an approximately normal curve. It will list your mean and the standard deviation. And once you have given someone the shape, the measure of central tendency, the mean, and the measure of spread or variation, the standard deviation, we consider that fully describing the curve or fully describing the distribution. All right, so this is an approximately normal curve. What would a normal curve look like? Well, I can show you how you can draw a normal curve if you want to. Let me put this up behind me. There you go. There is the formula for a normal curve. Does anybody want to work with that formula? No volunteers. Nora wants to know, what about skewed? Well, we are going to talk about how to avoid working with the skewed distribution, because our theoretical calculations depend upon a distribution not being skewed. So how do we avoid skewness? Well, let's talk about that. Good question. Let me pull up my bookmark here. And let me share screen.
Hi, I'm Patty Fraser-Locke, and this is a brief
and
introduction.
that is not the one I wanted to pull up. Sorry about that. There we go. This is what I'm looking for. Okay, if anybody still needs what I have on the screen right now, take a screenshot. Give you a few seconds to do that. Okay, and let's return to a website I have shown you before. And there you all are, but that wasn't one I wanted to show you. This is what I wanted to show you again. Let me move the chat out of the way as well. And let's begin. Because what we are going to be talking about now is sampling distributions. And if you have a approximately normal distribution of your original data, let's look at what happens. And this is set up for means. I don't believe it will do proportions, but proportions act similarly. So let me do this one. I'm going to find the mean of a sampling distribution. If I'm sampling 5 individuals, 5 values from here, finding the mean and placing it here and doing that repeatedly, and then at the same time, it's going to alternate as it does this, it's going to take a sample of 25 individual data points from this distribution, find the mean, and plot it somewhere down here. So if we take 5, repeat this 5 times. So 5 times it has taken a sample of 5 and placed it down here. And 5 times it has taken a sample of 25 and placed it down here. This looks nicely rounded, as does this one kinda. This one's skinnier. Okay, let's do it again for 5. Now this one looks pretty rounded there. This one's kind of getting spiky. Okay. And we keep doing 5 of these at a time. And you can see this distribution down here, the sampling distribution of sample size 25, becomes approximately normal much more quickly than a sample of 5. So let's clear these and look at a different distribution. Instead of having a nice standard normal distribution, what if we had something like this? Not normal at all. And if I just animate that, it pulls out 5, and there's the mean of the 5, and then it pulls out 25 individual values from our original distribution, finds the mean of that, and plots it on the lower line. So that I should have showed you first. But if we repeat that for a sample of 5 and a sample of 25 5 times, and another 5 times, neither one of them's looking very normal right now. Another 5 times, another 5 times. The sample of 25 is approaching normality more quickly. Now, by the time you get up to 10,000 times, both of them are approximately normally distributed. They look bell-shaped. Okay, but if you look, the mean of the original distribution was 13.57. The mean of this sampling distribution was 13.60, and the mean of this one is 13.54. So both of the means are approaching the population mean, but look at the difference in the standard deviation. This has a much smaller standard deviation, or as we actually call it when we're doing sampling distributions, standard error. So since we're going to be using that to calculate a margin of error, we want the smaller standard distribution. Excuse me. And so we'll want the larger sample size for this. So you can move from an original distribution that is not normally distributed, but we need to get to a approximately normally distributed sampling distribution as quickly as we can. So a large sample size helps us do that. So Nora, did that help a little bit? So we can deal with skewed or strange distributions. Okay, but we want our sampling distribution to be approximately normal. You are welcome, and thank you for asking, because I intended to go over that. Thank you for reminding me. Okay, so all right, so that's one of the things we need to do. Let me pull something from your textbook. Sorry, my computer's being a little slow today. Okay, so when we went to StatKey, it calculated the standard error for us. But now I'm going to show you a formula that will allow you to calculate it yourself. So for those of you who want to know exactly how things work, here it is. Okay. Right now we're going to be talking about a proportion. And when we're looking at sampling distributions, right now we are moving from and I'm writing this down because I want you to understand this and copy this and get it firmly planted in your mind. Right now we're moving from a known population. Finish one word before you start the other. Known population with a known population proportion, P. Okay, so we know P. We know what this is. So to find the standard error of a sampling distribution when you have a known population and a known population parameter, or population, which is a proportion in this case, you do the proportion times 1 minus the proportion divided by the n. And what's n? Do you remember? N is the number in the sample. And it is the number in every sample you draw from that proportion to form your sampling distribution. So let's turn to an example. Let's see. And if you will look at the file that I sent you today via email, we're actually going to go to example 2 first. Okay. So example 2, if you have that up, reads that a news network wants to conduct a survey to estimate what proportion of registered voters plan to vote for T. Levasseur, the presidential candidate of the revived Bull Moose Party, in 2024. They plan to survey 400 registered voters in their county. Now, we don't know what this parameter would be in a practical solution. In fact, I changed this to be a totally imaginary situation, unless, surprisingly, the Bull Moose Party comes back in 2024. While we wouldn't know this, we're going to suppose that when they do this sample, they get 65% of the registered voters in their county who say they will vote for the Bull Moose Party candidate T. Levasseur in 2024. So let's describe the sampling distribution. So we're going to mention all 3 parts of the sampling distribution, or the 3 descriptors. And we can start with that right now. Make sure you have that formula written down for yourself. I'm going to share a different screen now. Here is my screen with the example 2 right there. So first, we're going to do a sampling distribution. Now, there's one thing I didn't mention that I should have mentioned, so I'm going to put it in right here. I'm going to insert an equation, because you can use the equation that I gave you if and only if this is true. The sample, the number in the sample, times the proportion is greater than or equal to 10. And the number in the sample times the proportion, 1 minus the proportion is greater than or equal to 10. So what's that saying? What it's really saying is that you need to have a situation where you have a large enough percentage for your population proportion. You have to have a large enough population proportion that when you plug it in here and in here, combined with the number in your sample, you're going to have at least 10 individuals who say, no, I'm not voting for T. Levasseur, and 10 people that say, yes, I'm voting for T. Levasseur. You need to have at least 10 on either end of the spectrum, and you figure that out this way. And if you have that, then you can apply the formula, which was P times 1 minus P divided by N. Now, I'll make that bigger for you. Okay, so we can use this formula, and that is, I should have put what it's a formula for. Standard error. Okay, we can only use this formula if we have this situation. And that's what I wanted to show you. What happens if we do not have that to be true? Well, in your e-text, it gives you examples of what happens to that multiplication there, the n times p and the n times 1 minus p, for various situations. It won't let me. There we go. That's a little bit bigger for you. Okay, here we have a sample of 50, which is a decent sample size. But if you're trying to work with a very small proportion, p is only 5%, you don't get a nice normal distribution. You get a skewed distribution. So we'll talk about how you can kind of fix that. If you are using a proportion of 10% with a sample number of 50, it's a little less skewed. But by the time you get up to 0.25 or 25%, it's fairly normally distributed. So proportions that are closer to 50% work okay with a smaller sample. Now, without seeing this distribution, how could you figure that out? What happens when you multiply 50 times 0.05? Somebody do that on your calculator. What do you get? 50 times 5%, n times p. 2.5, it's less than 10, right? In order to use the formula, it has to be greater than 10. Now, what does n times 1 minus p? In this case, subtract this from 1, you get 0.95. So 50 times 0.95 gives you 47.5. Okay, so the not p is where more of the data is. So it is skewed. As you increase, you get values that are greater than 10. So this is pretty close. Could somebody do this one for me? 0.25 times 50. $12.5, thank you. Great, we're getting confirmations now. So it's more than 10, right? And 0.75 times 50? Because that would be 1 minus p. 0.75 times 50 gives you 37.5, yeah? All right. And 0.50 Very nice. As you move into 0.90, notice if this is P, this is 1 minus P. If P is 0.90, 1 minus P is 0.10, and just like this is skewed, this image here is smaller. It's squeezed horizontally. It's unfortunate, but you can see it's skewed in the opposite direction. And then when we get, I don't want to worry about the read aloud feature. Okay, 0.99%, yeah, that is hugely skewed because 1 minus P is 0.1 times 50. Yeah, that one's not going to work with a sample size of 50. In this case, we're holding, for these three, we're holding the sample proportion to 0.10, which with a sample of 50, whoops, sorry, went too far, here was skewed. Okay, couldn't do it. So if we just play with that proportion and change the sample size instead, with a sample size of 10, NP is going to be 1, right? With a sample size of 25, what do you get when you multiply 0.1 times 25? 2.5, right? Somebody do 200 times 0.1 and 1 minus P, which is 0.9 times 200. Or somebody's, please. So 0.1 times 200 should be 20, right? But what is 0.9 times 200? Great. 180. Yes, both of those are bigger than 10. You're going to have at least 10 individuals who do not say yes when you ask them a question, or they are not above a certain weight, or they are not a certain color. And you're going to have at least 10 that are that certain color, or are above that weight, or do say yes, whatever. Okay? So if you have a small proportion, you need to use a larger sample size to make a normal sampling distribution. If you have a proportion that's somewhere closer to 50%, usually between 0.25 and 0.75%, then both of those formulas here will be greater than or equal to 10. So you either have to change your proportion or change your sample size. Okay, so for this, let's describe the sampling distribution. Our proportion is P. So P equals 0.65, close to 50, that looks good. Okay, and our number, N, is 400. So N times P is what? 400 times 0.65, 0.26, yes. Confirmation? Oh, wait, Simon says no. 0.65 times 400, 260. Confirmation? Yes. Anybody else get 260? If you do 400 times 0.65, does anybody else get 260? Okay, great, thanks. Okay, and then we need to calculate N, which is 400, times 1 minus P, which would be 0.35. And what is that? 140, confirmation. All right, thank you. Okay, so it checks out. So I forgot to put that in there. Equals 260. Okay, and in both of those cases, this is greater than or equal to 10. So we can now work with this formula. And in place of P, we're just going to put in 0.65. And I could put in 0.65 here, but why not just say 1 minus 0.65 is 0.35? And our number is 400, the number in the sample. And what does that give us as an answer? The square root of 0.65 times 0.35 divided by 400. Okay, so Nora has us a little bit different. Huh. Okay, we have two candidates here. Which one do you agree with? 0.024 looks like. Okay, standard error. I think that's a more reasonable standard error given the numbers that we are working with. With a much larger sample, nor your answer could be correct, like at about 4,000 or something. 5,000? 10,000? Okay, so make sure you have the decimal places and all the... taking the square root. Okay, so we have the standard error now. And we could now draw this sampling distribution. So let's try this. Okay. Our mean of the sampling distribution is the proportion, right? So our proportion here of our sample, so it's p hat, would be the population proportion, because as we resample and resample and resample, the mean of all of the populations of our samples approaches the, that's interesting, population proportion. And our standard error here would be 0.024. Okay. Now, we have, let's see, this is where I want to go with it right now. Okay, so in order to write up this sampling distribution, or in other words, to describe the sampling distribution, you have to have three things. You have to have the shape, you have to have the mean proportion, and you have to have the standard error. So for this distribution, we would say the sampling distribution of voters, registered voters, Who plan? Come on. For T. Levasseur in the 2024, lost my number lock, presidential election. Is, what's the shape? Approximately normal. The sample proportion, or the mean of the proportions, we'll go with the mean of the sample proportions. We'll just write it all out. Is 0.65, and the standard error equals 0.024. So someone else could set those numbers up in StatKey now that I've given them that information. So let's go to StatKey. Let's see, I have it over here. Okay, and what we are going to look at right now is the sampling distributions. We haven't gone down here to look at these yet. Or actually, we have done the sampling distributions. I'm going to take you to the normal distribution in just a little bit. But let's look at a proportion. This is one they've given us. This is college graduates. We are going to edit the proportion. Okay, and our proportion is 0.65. Okay. And our sample size was 400. So I have this normally distributed. Okay, I have the proportion because, well, you have the proportion. I'm giving it to you. We work together to get these numbers. Sample size 400, proportion of 0.60, and let's generate 1,000 samples. What's the standard error? 0.024. There we have it. Okay, so we just did it with StatKey. You can now do it without StatKey. Now, I'm not giving you absolutely all of the formulas that you need. This is kind of like working with Word itself. I don't know how it's programmed. I'm not a programmer. I haven't worked on, I know there's programming going on as I use Word. And I know how to manipulate some of the things here and get it to do what I want it to, rather than just letting it do it automatically. It will set up margins for me, but I can change the margins. So that's kind of the level of stats you're at. It's kind of like working with a word processor. You know some of the things in this course. You'll learn some of the things you can do and adjust through these formulas. But there are many other formulas, like the one behind me, for the normal distribution that we just won't get to. We can't. In fact, in order to understand really where that formula comes from, you need calculus, because we're talking about the area under a curve, which is calculus. Let me take you back to StatKey for just a moment, though. That's not StatKey. This is StatKey. Now I have to admit something to you. Take a look at the theoretical distributions. And we're going to look at the normal distribution. No data will perfectly fit a normal distribution. That's why it's theoretical. But theoretically, you could have a perfectly normal distribution following the equation behind me. And we can do tails on these things, right? This is a normal distribution. In fact, this is the standard normal distribution. You can edit those to get it to not be the standard normal distribution, but this is good for our purposes right now. Let's look at where 95% of the data falls under this normal distribution by making it a two-tailed graph. What do you notice about this two-tailed graph? There's something funny about it. This is a perfect normal distribution. It's theoretical. Do you see anything that looks off? Take a look at all the numbers there on the graph and below the graph. They aren't exactly at 2, right? What we've been doing is not dealing with a perfectly normal distribution. We've been dealing with specific cases, specific data. So in general, when you are working with bootstrapping and everything, 95% is approximately at 2, because this rounds up to 2, right? Is okay. But now that I'm teaching you how to calculate this by hand, we're going to use this normal distribution and these specific numbers when we're ready to calculate confidence intervals on Wednesday. Okay? So now you're going to have more exact values and not just eyeball it, rule of thumb 95. Now we do a lot in stats with just rule of thumb. Like a rule of thumb is generally 30 in your sample. Even if you're working with proportions, will be enough to get an approximately normal distribution. We saw if the proportion is very, very small, you need a much larger sample. But in general, 30 is about a good size, but that's a rule of thumb. You have to then say, let's check 30. Does 30 give me a distribution? 30 individuals in my sample? Oh, it doesn't. So I'm going to have to sample more, take a larger sample for this. Okay. So for today, most of what you'll be doing with your homework, and go ahead and look at it so you can come back with any questions, because the Wiley homework is not due, of course, until Sunday. But do get started on it. Bring your questions back Wednesday, and we will look at taking all this information I've dumped on you today and using it to form a confidence interval for a proportion. Do you have questions for me? And if not, our time is up. I will see you Wednesday. Thank you for all your help.